The drill bit broke through the seabed, expecting nothing but ordinary mud, and pulled up solid, crystalline salt from 2 kilometers down. It was a physical impossibility that shattered the consensus of 1970 and forced a terrifying geological reconstruction. The entire Mediterranean once vanished, leaving behind a sprawling, sun-baked salt desert. The core extracted by the Glomar Challenger contained layers of halite and gypsum. These minerals require a saturated environment to precipitate, forming under an intense sun in a shallow, stagnant pan or on a dry basin floor. Yet here they were, buried beneath 2 kilometers of Mediterranean water. The laws of chemistry demand a contradiction. Either the water was not there when the salt formed, or the basin floor has behaved in ways modern geology cannot explain. This evidence leaves us with a specific, rigid demand. To deposit hundreds of meters of salt, the sea must have been removed, concentrated, and then replaced. We now face the reality of whether that sea returned in a single event, or if the Mediterranean was destined to cycle through these repeated phases of death and rebirth. The sheer scale of the shift forces us to look past simple oceanographic models and consider a cataclysmic history hidden beneath the waves. This was not a slow transition, but a violent erasure of an entire basin, followed by a sudden, drowning return of the tides. The evidence is now etched into the core samples, waiting to be reconciled with the timeline of the ancient world. This cycle implies a Mediterranean that was fundamentally broken. The math demands a physical mechanism to explain where the water went. If the basin was cut off from the Atlantic, the sea would lose volume faster than the rivers could replenish it. The remaining brine would shrink until the basin held only shallow, hypersaline pools, creating a desert landscape at the base of the world. We now have to determine if this was a singular geological tragedy or a recurring pulse. The evidence forces us to account for repeated evaporative events. One side of the scientific divide claims the basin desiccated entirely into a salt desert. The other side argues the sea remained deep but restricted by the closing of the Gibraltar corridors. Both theories rely on the sediment cores pulled from the seafloor. These cylinders of rock act as a timeline of a dying ocean. The researchers who first brought these samples to the surface were not looking for a lost world. They simply expected to find mud. Instead, Kenneth Jesus and William Ryan peered at the core and found a history written in fire and drought. The drill bit hit hard layers of gypsum, followed by dense crystalline halite. These minerals require a shallow, scorching sea to precipitate, yet they sat thousands of meters beneath the current surface. The math is cruel. To deposit such massive layers of salt, the entire basin had to empty and refill repeatedly. An ordinary evaporation of the Mediterranean yields only a thin veneer of salts, but these beds are hundreds of meters thick. They demand a replenishment of water that defies the logic of a closed system. If the sea was dry, something kept it separate from the Atlantic. If it was full, the salt could not exist. The basin was a machine of cycles, trapped between two worlds, with something opening the gate and slamming it shut again and again. Now, The question remains, what held the water back? The Mediterranean loses more water to evaporation every year than its rivers return. Without a constant influx from the Atlantic, the sea operates at a permanent deficit. If the gates were closed, it would vanish. 6 million years ago, the regional geography shifted as Africa drifted northward, driving the Gibraltar Arc upward and westward. Two ancient gateways, the Betic Strait in southern Spain and the Riffian Corridor in Morocco, began to constrict. Modern geography did not exist here. The basin remained tethered to the Atlantic through these narrow, shallow channels. Tectonic pressure squeezed these paths, choking the flow of life-sustaining seawater. As the restriction tightened, the basin could no longer stay full, and the drop began. With the inflow starved, the chemistry of the basin altered in a rigid, predictable sequence. Minerals do not precipitate from seawater in a random order. They fall out in a fixed line of succession. What settles first is not table salt. This chemical hierarchy serves as the primary clock of the crisis. This clock relies on physics, not luck. Clause 4. Every salt grain occupies a specific position dictated by the precise laws of thermodynamics. Clause 3. When seawater saturates, it discards minerals in a rigid, repeating order that no force of nature can override. Pause 5. This seafloor record preserves a chemical ledger of every rise and fall across the basin floor. We do not have to guess at the sequence because the strata act as an absolute temporal marker. Pause 6. The work has unlocked the internal mechanics of a dying sea, but it has also exposed a jarring problem for our current geological models. Pause 4. If you follow this investigation, subscribe to witness the evidence as we stress test the competing theories of the crisis. Pause 350 years after the first core arrived on the deck of the drilling ship. The data continues to challenge the basic assumptions found in our modern maps. Pause 5. We are not observing a simple geological oddity. Pause 3. We are investigating the fundamental stability of the entire Mediterranean basin. Pause 5. The question is no longer whether the sea vanished, but how quickly the Earth can rearrange its most enduring features. Pause 6 frames used: chemical ledger, thermodynamics, geology, basin stability, chemical clock, salt grain, mineral order, seafloor strata, temporal marker, epithets used. Chemical ledger, chemical clock, geological oddity, basin stability, absolute temporal marker. To read the basin, you must track the chemistry of the water as it failed. Seawater acts as a precise chemical ledger. As evaporation concentrates the brine, elements drop out in an immutable sequence. First come the carbonates, settling like fine dust. Then gypsum precipitates, forming dense, layered mats. Halite follows, building thick crystalline crusts. Finally, the bitter potash salts appear. This order is preserved within the seafloor strata. By examining the cores, researchers identified gypsum layers dating back to 5.96 million years ago. This is the fingerprint of a dying sea. Because that mineral sequence only occurs in restricted basins, it serves as an absolute temporal marker for the initial drawdown. The core samples provide proof that the water was not just shallow. It was undergoing a violent chemical transformation driven by the process of its own disappearance. If the gypsum marks the start of the end, it leaves a void in the record regarding what happened when the water vanished completely. The next task is to reconcile these layers with the physical reality of a desert floor. The salt giant is not a featureless expanse of mineral. It is an architecture of layers spanning over 1,000 meters in depth. Models suggest sea levels fell by more than 1,500 meters at the crisis peak, turning the Mediterranean into a deep, jagged canyon complex. The Nile and the Rhone rivers responded to this shift immediately, cutting their channels deep below today's continental shelves to find the new, vanishing base level. Those ancient river canyons are still there today, buried beneath the modern seafloor as hidden records of the desert that once thrived here. Yet, the core samples reveal that the salt is not a single, solid slab. It exists as alternating strata of halite and other minerals. This layering demands an explanation for how a drying basin could be interrupted. The basin was forced to record its own history in distinct pulses, suggesting that something was regulating the volume of the sea. The deep basin did not empty just once. Pause 4. That pulsing history was written into the seabed across many thousands of years. Pause 5. This duration is 3 times the entire existence of our own species. Pause 4. The rhythmic layers inside the core tell the story of a system trapped in orbital gears. Pause 3. As the Earth tilted and swayed, the Mediterranean responded to the cycle of the sun. Pause 5. Each time the gateway pinched shut, the water dropped until the sun claimed the basin. Pause 4. Each time the crust shifted, the Atlantic rushed back in to reset the clock. Pause 5. These were not singular events. Pause 3. They were pulses. Pause 3. Every shift in the strata marks a moment where life was forced to endure, retreat, or simply disappear. Pause 6. As the conditions within the basin grew increasingly extreme, the chemistry began to shift towards something entirely new. Pause 4. The salt layers were merely the backdrop for a much stranger transformation. Pause 5. Frames used orbital cycles, Earth tilt, seafloor strata, rhythmic layers, chemical transition, pulsing history epithets used. Orbital gears, trapped basin, extreme conditions, rhythmic record. By 5.5 million years ago, the basin chemistry shifts. Pause 4. The deep sea evaporites give way to distinct sediment layers. Pause 3. The water here is no longer a brine of concentrated sea salt. Pause 5. Increased rainfall and river discharge freshen the basin floor. This creates a vast, brackish, low salinity wilderness known as the Lago Mare phase. Pause 3. It mirrors the modern Caspian Sea more than an ocean, where freshwater-tolerant diatoms bloom in the shallows. Pause 3. One specific species, the Cyprideus turosa ostracod, thrives in these strange margins, marking the transition into a brackish wilderness. Pause 6. This biology is trapped in a precarious window of time, evolved for a habitat that cannot survive the next tectonic twitch. Pause 5. Their existence is a countdown. They are living on borrowed time before the seal breaks and the deep sea returns to reclaim its territory. Pause 6. This specialized world holds an expiry date written in its own chemistry. Pause 5. The extinction of this specialized fauna serves as the ultimate biological proof of the basin's total isolation. As the water vanishes, the air above the basin undergoes a transformation of its own. Pause 4. As the water retreated, the basin floor became a deep, sunken laboratory of extreme thermodynamics. Pause 4. Air dropping into this depression compressed under its own weight. Pause 3. Gravity pulled the atmosphere down, crushing it into a dense, superheated mass at the nadir of the salt plains. Pause 5. Physics dictates this temperature spike. The air at the bottom warmed in direct proportion to the depth of the void. Pause 4. Sunlight baked the exposed halite until temperatures surged to nearly 50 degrees Celsius. Pause 5. The basin floor transformed into a hyper-pressurized, scorching furnace. This heat and density created a barrier more absolute than any mountain range. Pause 3. Every living thing on the surface faced an impassable wall of searing, heavy air. Pause 5. Life retreated to the fringes of the basin to survive the heat. Pause 4. Yet while the center turned into a kiln, the edges remained dynamic zones of contact. Pause. Creatures, sensing this change, began to move across the drying margins, seeking paths across a landscape that was only briefly firm underfoot. These margins were not empty. Paleontologists track land mammals crossing between Africa and Iberia throughout this interval. These species did not require a fully dry basin floor to migrate. They utilized the narrowing gateways and the transient land bridges that emerged as the sea retreated. One leading model places this primary terrestrial corridor across a volcanic archipelago in the East Alboran Basin. It acted as a filter bridge, selectively permitting passage for hardy, mobile fauna while closing off deep water transit for the rest. Hominids played no part in this epoch. Our ancestors arrived millions of years after these salt flats were buried and the sea returned. The story of the crisis is written in geology, not in the traces of human survival. The primary evidence rests upon the crustal shifts that strangled the Mediterranean. Even as the data solidified, a sharp divide emerged among the experts. Was the basin truly an empty, salt-crusted desert, or did it remain a deep, restricted marine pocket? Yet this picture of a salt-starved, parched interior remains a lightning rod for debate. A 2025 review challenges the bedrock of the entire desiccation model, questioning if the Mediterranean truly emptied to its floor or if it remained a deep, restricted marine pocket. Proponents of the desiccation case point to deep river incisions and the massive volumes of halite buried beneath the abyss. Critics, however, argue that these same markers could persist in a basin that never lost its connection to the Atlantic. They suggest the gateway at Gibraltar was never fully severed. It remained a narrow water gate, restricted but alive. This active investigation tests the limits of our geological reach. Both camps acknowledge one final point of violent intersection, agreeing that whatever the state of the basin, the threshold of the Mediterranean changed forever in one catastrophic event. The question of what forced that final rupture remains the most contested trigger in Earth science. Beyond the data of the salt layer, the mechanism of that rupture remains debated. Pause 3. One theory points to tectonic instability deep below the seabed. Pause 4. Crustal stresses may have triggered a slab tear beneath the Bedic Range. Pause 4. This shift could have forced a sudden massive failure of the Gibraltar Gateway. Pause 5. Yet other researchers favor a slower, more subtle cause. Pause 3. They point to constant seepage from the Atlantic. As water leaked through narrow fissures, it eroded the rock over thousands of years. Pause 5. This persistent cutting eventually compromised the sill's structural integrity. Pause 4. Whether the failure was a violent tectonic snap or the final result of persistent erosion, the outcome was inevitable. Pause 5. The sea was rising on the other side of that mountain wall. Pause 4. Gravity was already waiting to claim the empty basin. Pause 6. The geological record shows the exact path that water followed as it returned. Pause 3. It cut a trench deeper than any canyon on Earth. Pause 4. Frames used: Tectonic slab tier, Bedic structural integrity, Atlantic seepage, Gibraltar sill erosion, Zanclean channel geometry. Epithets used: crustal stress, persistent leakage, inevitable rupture, empty basin, gravity-driven collapse. The evidence of this transition lies etched into the bedrock of the Strait of Gibraltar. Pause 5. There, a massive canyon stretches for 200 kilometers, a gaping scar gouged into the crustal stress of the region. Pause 4. It is incised over 250 meters into the seafloor, tracing the path where the Atlantic reclaimed the basin through the Zanclean channel geometry. Pause 5. This is a record of kinetic erosion carved by inevitable rupture. Pause 5. When the threshold failed, the Atlantic surged inward as a discharge of massive volume every single second. Pause 6. That flow is 3 orders of magnitude larger than the volume of the modern Amazon River, carrying the immense energy of a gravity-driven collapse. Pause 5. The sea did not merely return. It fell into the empty basin. Pause. Within the abyss, the water level climbed at an extraordinary rate, with models indicating a rise of up to 10 meters every single day. Pause 6. It was an ocean-scale surge that buried the salt desert, marking the sudden catastrophic failure of the persistent leakage that had once defined the gateway to the Mediterranean. Pause 5. That sheer volume of water did not enter as a steady trickle. Modern simulations suggest the refill unfolded with terrifying speed. 3. The initial breach was narrow, yet it triggered a runaway feedback loop. Pause. As the incoming Atlantic current scoured the channel, it stripped away the rock base. Pause 4. The passageway widened and deepened with every passing hour. Pause 3. Discharge rates accelerated toward massive volumes per second. Pause 6. At the height of the inundation, the sea level inside the basin climbed by 10 meters every single day. Pause 5. What was once an arid basin became a rising tomb. Pause 4. This sudden influx did more than just drown the salt desert. Pause 3. It fundamentally annihilated the unique hypersaline environment that had defined the Mediterranean for hundreds of millennia. 5. The waters reclaimed their dominion, yet they brought with them a total erasure of the basin's previous character. Pause 4. The specialized life forms that had adapted to those desolate, landlocked conditions faced an instant, violent end. Pause 6. The very mechanism that restored the sea also functioned as an evolutionary reset switch. Pause 5. Frames used: Zanclean channel expansion, rapid discharge kinetics, volumetric sea level rise, abrupt environmental transition, biological extinction pressure. Epithets used: runaway feedback loop, rising tomb, total erasure, evolutionary reset switch. violent end, the flood did more than restore the depths. Pause 3. It terminated a distinct chapter of biological isolation. Pause 5. For hundreds of thousands of years, the basin's brackish, landlocked waters fostered a unique ecosystem. Pause 6. Organisms like the ostracod, Cyprideus turosa, thrived in these hypersaline, unstable environments, evolving into specialized forms found nowhere else on the planet. Pause 6. When the Atlantic waters surged through the Gibraltar Channel, they brought the full ocean ecosystem with them. Pause 4. This influx replaced a fragile, highly adapted world with a vast, open marine reality. Pause 5. The species that had defined the Lagomare phase were overwhelmed by the returning tides, their localized reign ending in a heartbeat of geological time. Pause 6. As the pressure equalized and salinity normalized, the basin underwent an ecological purge. Pause 4. The record of this shift is locked beneath the seafloor, buried under layers of sediment and millions of years of accumulated history. Pause 5. We consider the physical permanence of these deposits a silent, buried legacy of a world that vanished when the gates were forced open. Pause 3. The legacy of that ancient evaporation exists today, not just as a record in the stone, but as a resource beneath our feet. Pause 4. Across the Mediterranean basin, the industrial extraction of halite is a direct harvest of the Messinian salt giant. Pause 3. Sites in the Sicilian basin and Real de Gandia tap into these buried layers, pulling out massive quantities of salt every year. Pause 5. This material is far more than a simple chemical product. It is the physical remainder of a crisis that reshaped an entire region. Pause 4. Yet, the sheer scale of this accumulation forces a confrontation with the limits of our models. Pause 3. We have documented the strata, mapped the canyons, and measured the isotopic signatures left behind in the rock. Pause 5. Still, we reach a point where the evidence diverges into two competing narratives about the basin's actual state. Pause 4. The data is final, but our interpretation of its history remains in flux, leaving us to weigh the gravity of a desiccated desert against the possibility of a deep, brine-filled abyss. Pause 6. Yet this chemical record is anchored by one certainty. A salt giant nearly 2 kilometers thick sits beneath the Mediterranean floor. This formation was governed by a tight rhythmic cycle between 5.9 and 5.3 million years ago. It required the basin to reach a critical threshold of aridity that left the deepest seafloor an exposed, hypersaline plain. The terminal breach that ended this isolation remains mapped on the seafloor today, where the channel carved by the incoming Atlantic flow shows the path of the Zanclean flood. Still, the debate over the intensity of that desiccation survives. Some models argue for a near-complete dry-out, while newer findings suggest a restricted but water-filled deep basin. Science is an ongoing process of refining the scale of these past catastrophes. We have the crystalline record, the canyons, and the date. The discrepancy between these facts is where the next generation of researchers will focus their geological calibration. This is the weight of 50 years of studying these tectonic gateway models. The Strait of Gibraltar acts as the singular choke point between the Atlantic and the Mediterranean. At 14 kilometers wide, it dictates the salinity and the life of an entire sea. The geology here is a history of closing that door and ripping it back open. Some models focus on the tectonic slab tear deep beneath the bedic mountains as the trigger for the initial restriction, while others look to the progressive erosion of the sill by Atlantic currents as the ultimate failure mechanism. Both schools of thought reach for the same physical evidence: the massive underwater canyon incised into the floor of the strait. This channel remains a witness to the exact moment the basin reached its breaking point. As the threshold of the Mediterranean changed, the hydraulic geometry of this gate determined everything. We must look closer at the specific mechanism that failed to hold the Atlantic back, as the next piece of the investigation requires mapping the precise tectonic forces that govern this narrow gateway. These tectonic movements dictate the survival of the entire inland sea. Its stability is an illusion written in shifting plates. Should those plates grind shut again, the Mediterranean's water deficit would begin its extraction process within a human lifetime. The basin is not a permanent feature of our world. It is a transient depression currently held open by the grace of a 14-kilometer gap. The layers of salt hidden beneath the mud are not merely a history of a distant epoch. They are a warning of the basin's potential to vanish. If the Atlantic inflow falters once more, the cycle of heat, evaporation, and desolation will reset. The sea will retreat to the lowest depths. The canyons will emerge from the dark, and the salt giant will begin to grow again, burying the world that exists above it. Geography is never final. It is merely the current state of a struggle between the crust and the tide.